and may I request you to introduce yourself so that we can proceed with the question answers.
Sure. So hi, everyone. My name is Claire Lee. I am a particle physicist. I was born and raised in South Africa. And I moved over here to CERN in 2011 with my family to complete my PhD on the Atlas experiment. So I worked on the Atlas experiment for about 12 years. And then I moved over to work for a lab called Fermilab, which is actually a lab based in the United States. But I'm still based here at CERN. So I spent a bit of time working on the DUNE experiment, which is a neutrino experiment that's under construction in the United States. And since November last year, I am now working for the CMS experiment, which is like the Atlas experiment. It's just the other one of it. It's the better one. My husband's upstairs going, because he works for Atlas. So it's like the two experiments, they're like friendly competition. They're both designed to look for similar things at the LHC. So, we've got this kind of competitiveness going between us, but also it's nice to have, a second experiment, because if you both see something new, then it gives you extra confidence that, what you're seeing is actually real, which is what happened with the Higgs discovery. So there you go.
Before I invite my students to interact with you, I would like to request my head of the institution and to come forward and speak a little bit with you. And it is my privilege to invite the head of the institution.
Great.
Hi, good morning. I am the headmaster of this institution. I am Mohan Rao.
Hi.
My name is Lohita Girija. I am a 10th grader from Z.P.H.S Ilavaram. I am blessed today to interact with you. I like science, especially physical science. I have a question. Can I ask you a question, ma'am?
Yes, absolutely. Looking forward to it.
What kind of success has the Atlas experiment achieved so far? How long will it take to achieve its desired goal?
That is a really great question. So I have some slides. Can I share my screen? There we go. So I got sent all the questions before, so I could put some slides together. Let me skip forward. No, to your question. Okay. So there was also a question about what is the Atlas experiment. So is it okay if I start there and then follow up with your question afterwards about, what Atlas has done?
Okay, ma'am.
Okay, fantastic. So what we need to talk about when we're talking about the Atlas experiment is one of the 4 large experiments at the Large Hadron Collider at CERN. So the Large Hadron Collider is an accelerator that sits 100 meters underground in the Swiss French Valley. And the point of the accelerator is to take protons, and they fill the accelerator up with protons going in 2 directions at once. And then they speed these protons up faster and faster and faster until they're going to almost the speed of light. And once they're going at almost the speed of light, they let the beams in both directions cross over and the protons collide. And then, the protons collide, they squish together, they can create a bunch of things, and we see whatever it creates, we can see, flying outwards from the collision point. So there are 4 collision points, and at each of these points, we have built these huge, big particle detectors, which are basically like big 3-dimensional cameras that are taking snapshots every 25 nanoseconds. So that's 40 billion times per second. because that's how fast these protons are colliding. And the detector is basically taking a snapshot of what is coming out of the collisions. So ATLAS is one of these 4 big detectors at the LHC. So this is a photo, this is just a photograph of inside the Large Hadron Collider tunnel. These blue tubes are superconducting magnets. There are 1,232 of them all the way around the 27-kilometer ring. And they help keep the protons bending around in a circle. So they go round and round and round again. So, okay, so just here's a little animation of how it works, how the LHC works. So we don't just stick protons in the LHC and then boom, go. There's actually a few steps that are involved. First, we actually just start with a tank of hydrogen gas. And hydrogen is 1 proton with 1 electron. So if you take the electron away, then you're just left with a proton. And so we send these protons from a tank of hydrogen gas down a linear accelerator. And then these go into a little booster, which they get a little bit of energy. And then they go into a bigger accelerator called the proton synchrotron, which used to be CERN's biggest accelerator. From there, they go into the super proton synchrotron, which used to be CERN's biggest accelerator, and get even more energy. And only then are they fed into the LHC. So then they're going around in 2 directions. So here we kind of zoom into the tunnel. We're going along the tunnel. Oh, we've just crossed the border between France and Switzerland. Luckily, we don't have to share, protons don't have to show their passports. This is a proton. It's a schematic of a proton. And coming up to one of these collision points, if the LHC people manage to get the focusing and the alignment just right, then these protons can collide in the center and, send sprays of particles outwards, which we catch in our detector. So that is, basically how things work. And this is a photograph of the ATLAS detector, the ATLAS experiment. And the thing about these detectors, the way that we've built them is in layers. So each layer is designed differently, and each layer measures something different about the particles as they move through. And when we put the information from all the different layers together, then we're able to get an idea of what kind of particle it was coming out of the collision. So this is, this is a picture of an actual event. So you're looking sort of down the length of the barrel here. The protons come from inside outward. They collided in the center, and every one of those yellow lines in the center shows the track it's basically where a particle went, like flying outwards from the collision point. And those big colorful bars, that shows that we had a large number of particles spraying in that direction and spraying in the opposite direction. We call these jets of particles. And that was like that. So this is an actual picture of an actual event that happened a couple of years ago, I think, in ATLAS. In fact, I actually have an umbrella with this picture on it. So this is a schematic drawing of the ATLAS detector, and it shows all the different layers. So because the protons collide head on, things mostly come spraying outwards, like that. So you want to build things to catch. So the way that we build it is like a cylinder, and then we've got, which we call the barrel, and then we've got what we call end caps, which is like the lid in the bottom of the barrel, just to catch the stuff that goes out the side. So every layer comes in a barrel and an end cap form. So right inside the center, we have tracking detectors, which let the particles move through, and then you get like really, really, really precise position measurements for these. Around the tracking detectors, we have what we call the calorimeters There's actually two different types depending on the type of particle that comes in. And the calorimeter's job is to stop the particle. And when you stop the particle, it's like if you drive a car into a brick wall, don't try this at home, please, or anywhere. But if you drive a car into a wall, bam, then the bricks go scattering outwards. And if you count up how many bricks there are and how far they got scattered, that will tell you about the energy that you had in your car that you were driving, your energy. And it's the same thing here in the calorimeters. We stop the particle in the calorimeter, bam, and we get a shower of light being produced. And we have special sensors that collect all the light and measure the light, and that tells us how much energy the particle had. So now we've got position, we've got energy. Right around the outside, there are what we call the muon detectors. Muons are little particles. They're like electrons, but they're heavier. So they're like a heavier version of an electron. And they actually go all the way through the calorimeters without getting stopped. So we have basically more tracking detectors, but bigger versions all the way around the outside. So everything else will get stopped inside the detector. And then if we see some signals in the muon detector and some signals in the tracking detector on the inside, then we know that that's a muon. And then finally, we have magnets. And so the magnets create this really strong magnetic field. And the reason for that is that we can bend, positively charged particles will bend one way, negatively charged particles will bend a different way, and neutral particles will go straight. So we're able to tell the position, the momentum, the energy, and the charge of each type of particle, which is everything that we need to know to be able to tell the difference between the types of particles. If you take a wedge out of the detector, this is pretty much what it looks like. So these are the type of particles that live long enough to come through our detector. Making a Higgs boson, we actually make a Higgs boson every billion collisions, every 1 billion times protons collide inside the LHC, we can create a Higgs boson. But that Higgs boson only lives for a billionth of a second before it turns into other particles like photons or electrons or muons. And those are the things that we see moving through the detector. So this is just a schematic of what the different types of particles look like when we're inside the detector, as they're moving through the detector. So you can see that we're able to tell the difference, for example, between an electron, which gets bent in one way, and a proton, which is the opposite charge, and it gets bent in the opposite direction. Okay, so to come to your question, what kind of successes has the Atlas experiment achieved, and how long will it take to achieve its desired goal? So I would say, I think the Atlas experiment has achieved many successes in many different ways. And one of the goals, the ultimate goal of building a machine like the LHC with detectors like Atlas and CMS is to measure and learn more about what the universe looks like in this particular energy range that we can access with the LHC. So that is the goal. So, whether or not we discover particles or something, we're still learning more about what the universe looks like in this region. And so from that point of view, it's been a fantastic success. And we've already learned so much about the universe, and we're learning more and more and more. If we want to talk a bit more detail, so the first thing when we turned on the detector, we have to make sure that it worked, right? So that was the very first success. So way back in 2010, when we started taking the first data with the detector, what we did was we made a plot that looked like this. So this plot looks complicated, but it's not really complicated. It's basically just a counting plot. And most of the particle physics plots that you will see, if you ever look at a particle physics talk, you will see something that looks similar to this. So what's going on here? So on the x-axis, we are looking at, we're trying to measure something. So in this particular plot's case, it says m mu mu, so mu stands for mu1. So what we're looking at here is we're looking at events where we get two muons, and we take those two muons, and we add up their mass. Because if you have a particle that, you know, that turns into two muons, then the particle's mass is going to be divided up and shared between the two muons. So if you add the two up, then you'll get the mass of the particle. So on the x-axis, on the horizontal axis, that is what we're measuring. So we've got a scale going from, you know, less than 1 to almost to over 100 there. On the vertical axis, that very complicated looking label on the vertical axis is just, you know, it's just a mathematical way of saying I'm counting the number of times I get two muons for each mass that I'm looking at. So what happens is I take my data and I look through my data and I find my first event that has two muons, and I say, okay, cool, add them up and I get a number, let's say 1. And so when I go to number 1 on the horizontal axis, and then I say, okay, and I put a dot at, you know, I say, okay, I've got 1 event. And then I do it again. Maybe then I see another 2 muon event that adds up to 1. So then I take my point, and instead of being at 1, it goes up to 2 and up to 3, 4, 5. And as I work through the data, I'm going to get a lot of, you know, different numbers, different masses, and they're going to build up over time, because, you know, randomly you get 2 muons, and there's this like smooth curve that shows just all the random 2 muon stuff. But what you might also notice is that on top of this smooth curve, I don't know which way we're looking, on top of the smooth curve, we also have these spikes. And in a particle physics plot like this one, whenever you see a bump or a spike, that means that you are looking at a particle. Okay, so spikes mean particles. That's like, we literally call it bump hunting in some analyses, because you literally just, you know, making a plot similar to this and looking for a tiny little bump. And what's going on there is that if you have a particle that weighs, for example, 3 GeV, then that particle turns into 2 muons, then more than the random number of events, you will get an extra number of events at the, you know, creating a bump at the mass of that particle. So that's why if you go to 3 on that scale, you see a little bump, which is a particle that we call the J psi. So the very, very first, besides, you know, just building the thing and having it turn on in the first place, the very first physics success of the ATLAS experiment was that we made this plot. We saw all the bumps where they were supposed to be, which tells us that our measurements, the way that the detector was measuring particles was correct. And also the height of the bump was what we expected. And that was telling us that we were catching all of these particles that we were expecting. We weren't missing some. And both of those things are very important to be sure of before you go and start to look for new particles. So that was the first success of ATLAS. So then, have you heard about the Higgs boson?
No, ma'am.
Okay. Oh, okay. Fantastic. So before we go to the Higgs boson, I'm going to go back and talk a little bit. Oh, where'd my thing go? I'm going to go a little bit back and talk about some particles, if that's okay with you. And then we'll get to, one of the hugest successes of the ATLAS detector, which was the discovery of this thing called the Higgs boson.
And your name is also there. Your name is there and with flowers.
Oh, that's beautiful. Thank you. That's lovely.
Hi, ma'am.
Hello.
I'm Mahalakshmi. I'm in 10th grade, Z.P.H.S Ilavaram. I'm so glad to be with a wonderful scientist. I have a question, and my question is, what is considered the tiniest particle in the universe?
That is a really interesting question. So, okay. So, have you heard about atoms?
Have you heard of that? Yes.
No.
Physics, physical science. Atoms.
Yes, ma'am.
Yes. Yes.
Okay, great. So an atom has a nucleus in the center, and it has electrons that are orbiting, going around it, right? Now, an electron is one of the tiniest particles in the universe. In fact, we actually, it doesn't have a size. It's like drawing a dot on a piece of paper. It doesn't have a size itself. So that is one of the smallest particles. Now, the nucleus of the atom has protons and neutrons inside it. And protons and neutrons, they are big because they are made up of other particles, which we call quarks. So in here, you see this diagram here, we've got 3 quarks making up a proton. Now, the proton has a size, but the quarks also are like dots on a piece of paper. So they basically don't have size. We just call it a point particle. So that also is a very, very small, one of the smallest particles of the universe. In fact, if we break things down into the basic set of particles that you need to make up everything, we get what we call the standard model of particle physics. And basically all of these are the smallest particle because they all have, they're all like dot particles. They don't have size. So around the outside of this ring, we have matter particles. So these are the particles that make up stuff. So the red ones are the quarks. And there's actually 6 different types of quarks, and you only need 2 of those types to make up protons and neutrons. And the green ones at the bottom, those are the leptons. That E over there, that's our good old friend, the electron. And the mu one that's next to the E, that's the muon. That's like the heavier version of the electron. And then we actually have an even heavier version of the electron, which we call the tau. One of the mysteries of particle physics is why we have 3 sets. So we have 2 quarks. So 2 quarks and one electron, that's 1 set, and 1 neutrino, that's 1 set. And for some reason, the universe has given us 2 additional sets, each one heavier. But we don't need that to make the universe, we don't know why there's these 2 extra sets. That's a mystery that we're still trying to solve. And then on the inside, we have what we call the force particles. So in particle physics, everything is done by forces. So you have, everything is done by particles. So you have particles which, make up stuff like, my phone. And then you have particles which carry forces. So you know how you have if you have 2 charged protons, and then and then they repel each other. The way that they do that is by, exchanging particles, exchanging photons, which carry this force in between them. So everything is particles. And in this diagram here, all of these particles have no size. So they are the smallest particle, if you're thinking about things in terms of size. But another reason why that was a really good question is because when particle physicists talk about, like if a particle physicist says, oh, a neutrino is really, 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 really tiny, they're not actually talking about the physical size of the particle, but they're talking about how easy it is for that particle to interact with other particles. And if we're talking just about interactions, then the tiniest particle is something that we call the neutrino. That's those ones in green at the bottom, the nu, tau, nu, mu, nu, e. And the reason why neutrinos are so tiny, are so tiny in particle physics speak, is because a neutrino does not like to interact with other matter. In fact, the sun is producing trillions and trillions and trillions of neutrinos every second, just, while it's burning its fuel and creating light for us. And these neutrinos are streaming down and they're coming through us, and they are passing through our bodies. Trillions of neutrinos are going through you right now, every second, doing nothing. In fact, over your entire life, of the trillions and trillions of neutrinos that pass through you every second, in your lifetime, maybe one neutrino will actually hit an atom in your body. And so from that point of view, that makes neutrinos the smallest particle in the universe.
How do we measure the galaxy's distance?
So, sorry, I missed that. There was a bit of noise. Can you just repeat the question?
How do we measure the galaxy's distance?
That's a great question. All right, let me go to that slide quickly. All right. Go away. I don't want to see that anymore. Okay. So how do we measure a galaxy's distance? So this is a really, really interesting question. So you might have heard that when stars get to the end of their life, some of them explode, and that is called a supernova. So there are different types of supernova, but one type of supernova happens and it always explodes with the same brightness, no matter what. So it doesn't matter what star it was or how far away or whatever. When that star explodes, it explodes with the same brightness. So this provides us with a really easy way of measuring distances across space. Because imagine if you have a torch, right? And imagine if you had 100 torches and they were all exactly the same brightness and you knew how bright that was. If then you gave them to 100 friends and they all ran off around a field at different distances far away, then the people who were holding the torch close to you, their torch would look very bright, and the people who are further away from you, their torch would look dimmer. But because you knew that all the torches were actually the same brightness, then you knew that if I saw it looking dimmer, it meant it was further away. And with just a little bit of mathematics, you could calculate exactly how far away that is. So one of the ways that we measure distances for galaxies is we look at supernova. So this is a picture of a supernova exploding in a faraway galaxy. And because we know the brightness of it, of what that is supposed to be, we're able to use that brightness to work out how far away that galaxy is.
Hello ma'am, my name is Rohini Kanti. I am studying 10th grade from Z.P.H.S Ilavaram. I am so lucky to meet a great scientist. Can I ask one question, ma'am?
Absolutely.
Why is sky dark at night?
Sorry, can you repeat again?
Why is sky dark at night?
Ah, that's a great question. That is a very, very good question. So, why is the sky dark at night? So, if you think about it, the sky is light in daytime because we have a sun that is shining light at us. Cool. Now, at nighttime, the Earth has rotated, so the sun is on the other side, fine. But we look up into the sky and we see many, 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 many stars in the sky. And those stars they're just like suns, but further and further and further away. So if the universe was infinite, then we should have basically the entire sky covered with stars and light from those stars reaching us. And it should actually look like the sky is light at night as well, because there are, because the universe is really, 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 really big, and there are really, 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 really huge number of stars in the universe. So why doesn't it? So that the reason is because, yes, the universe is really, 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 really big, but it has not been around forever. The universe has only been around for almost 14 billion years, which sounds like a long time for people like you and me who live less than 100 years, but for a universe, that's actually a really small amount of time. And one of the reasons why the sky is dark is, yes, there are stars in all directions, but the amount of light that has come to us has not had time to build up that much since the beginning of the universe. So we still see it as dark. So that's reason number one. The other reason is actually there is electromagnetic radiation coming to us from all parts of the sky. It just so happens that that electromagnetic radiation is not the visible light that our eyes see. So light comes in different wavelengths, and there's only a very small band. You see that little rainbowy part right in the center there? That's the small part that our eyes can see. But there are different kinds of waves. There's ultraviolet waves, X-rays, gamma rays at higher energy, and then lower energy, we have microwaves and radio waves. Our eyes can't see microwaves and radio waves, but we can build detectors that can. And that's what this picture is here. This is one of the very first antennae that was built to pick up microwaves. And when they pointed that at the sky, You see, you can see like the galactic plane in the center because there's just extra amounts. But all of that green shows microwaves coming at the Earth, landing on the Earth from all directions. And this is a picture from, I think, back in the 50s or 60s. Today's picture looks like this. And the difference between the red and the blue is just it's a tiny, tiny bit of difference. But the point is that this picture is showing microwaves coming at us from all the way around the universe. So actually, if our eyes could see microwaves, then the sky would not be dark at night. Then, we would see, lots and lots of stuff at us, coming at us, all the way around at night. And this picture here, what this is actually showing is light that was really, really high energy gamma rays left over from the Big Bang. And over almost 14 billion years, that light has cooled and become microwaves. And that is what we're seeing now. So this is leftover light from the Big Bang that, with a microwave detector, we're able to see, but not our eyes. So 2 reasons why we can see why the sky is dark at night. One is that the universe has only lived for 13 billion years, so the visible light had a chance to catch up to us, but also because our eyes only see visible light, we're not seeing all of this stuff that actually is there. Is that helpful?
Yes.
Thanks.
Morning, ma'am.
Hello.
My name is Navyasri. I am studying 10th grade in Z.P.H.S Ilavaram. I am
Awesome.
proud of you as a God.
Oh.
It is a golden opportunity for me to ask a question.
Yes, please.
Could you please tell us about quarks?
About quarks. Yes, absolutely. Quarks are super cool. So let's go back to this picture, right? So the red things in this picture are the quarks. And there are 6 of them. We get 6 different types of quarks in the universe. But to make something like a proton or a neutron, you actually only need 2 types. Now, quarks are really interesting because they have, how an electron has charge -1 and a proton has charge +1, right? A quark actually has a fraction of a charge. So up quarks have 2/3, +2/3, and down quarks have -1/3. So that's why a proton has a +1 charge, because a proton is 2 up quarks and a down quark. So that's +2/3, +2/3 -1/3, you get, +1. Whereas a neutron is 1 up and 2 down quarks. So you have +2/3, -1/3, -1/3, and you get 0. So that is why a neutron has 0 overall charge. So this is like this is the basic view of a proton, and these are the 3 in physics world we call them valence quarks, because they are the quarks that give the proton its characteristics like charge. But an interesting thing happens at the Large Hadron Collider, because when you take something and you speed it up, like we're doing at the LHC, what you're doing is you're giving it more and more and more energy. And in science, higher energy is like a microscope that can look deeper. And If you've ever, have you ever had an X-ray? Have you ever broken a bone when you did an X-ray?
Yes, ma'am.
Okay, right. So an X-ray is just a higher energy type of light. So normal light, the visible light, is bouncing off the outside of me and going into your eyes, and then that's how you see me. But when you take X-rays, X-rays are higher energy, so they go deeper into you and you can see the inside structure. So higher energy means you can look deeper in and see more structure. So when we take protons and we speed them up to the speeds that they're going inside the LHC, a proton actually looks more like this. So we've got those big balls there. Those are the 3 valence quarks, the 2 ups and the down. But we've also got lots and lots of other little quarks. And it's a quark anti-quark pair that pops in and out of existence. And this is a funny thing about the universe. Everywhere in the universe, even in outer space where there's nothing, you can get matter, like a matter-antimatter pair, just being created from nothing, like boom, and then they go and they attract each other and they annihilate back into nothing. And as long as that happens in a short enough period of time, Mother Nature's like, you know what? I'm going to pretend I didn't see that. Whatever, you just do your thing. As long as that happens in a short enough period of time. This happens all the time. You have these matter-antimatter pairs popping in and out of existence. So this is happening inside protons as well. And when we speed the protons up to the energies of the LHC, we can actually start seeing those additional little quarks. And those spirally things there, those are gluons. That's the particle that holds the protons together to make the the gluons are the little particles that hold the quarks together to make up the proton. So this is why it's so much fun to smash protons at the LHC, because you're not just like smashing a ball, like 2 balls together, right? You're smashing things that have lots and lots of things inside. So when they smash together inside the Large Hadron Collider, any quark or gluon from this one and any quark and gluon from this proton can fuse together and form something new. So that's a little bit about quarks. Quarks are super cool.
Thank you, ma'am. Hello, ma'am. My name is Harika. I am studying 10th grade from Z.P.H.S Ilavaram. I am so happy today to be able to interact with you. I am going to ask one question, ma'am.
Yes.
Could you mind telling us about dark matter?
Absolutely. Okay. So, dark matter. What is dark matter? Well, okay. So, first of all, how do we know that dark matter exists? Well, one of the things that you can do when you look out into space is you can look at far away objects, like faraway galaxies. And if there's a galaxy cluster or something in between you and that faraway galaxy, then the light is going to get bent as it travels past that nearby cluster. It's kind of like how if you wear glasses, you've got a lens and the light gets bent as it travels, through the glass. So we call this gravitational lensing because it acts like a lens. So the light from the faraway galaxy is getting bent around, and the amount that it gets bent by tells you about how much matter is inside this cluster in between. Now, what people have done is, so this is actually, there's a picture on the right-hand side where you see like there's a galaxy in the middle, and then this round looking thing there. That is the round thing is actually a picture of a galaxy that has been smeared out to look like a circle because it's been bent around this cluster in the middle. Now, if you work out the amount of stuff that should be in the cluster to cause that amount of bending, you get one number. And then if you look at the cluster and count up all the stuff you can see, you get a number that is much less. In fact, it's about 1/5 of the total amount. So in other words, there's like an extra amount of stuff inside this cluster that we are not seeing. And that is what we call dark matter. So dark matter is stuff, it's matter, it's particles, it's something, right? And it has mass, so it creates gravity, but it does not interact with normal matter in any other way. So the reason why we call it dark is because photons, so to see something, a photon has to bounce off something and come into your eye, right? Like, so I interact with photons because they bounce off me. But if I was made of dark matter, the photons would just travel straight through me. Yeah, nothing. And then you would not be able to see me because the photons are not bouncing off me. So dark matter is, we call it dark because the photons light just travels straight through it. It doesn't bounce off it. The only way we know that dark matter is there is because of gravity. But we've got so much evidence for it that in fact we're able to calculate how much dark matter there is in the universe. So normal matter in the universe makes up about 5% of the universe. Oh, wait, let me do this. Can you, I don't know if you, so it makes up about 5% of the universe. But the rest of the universe is made up of dark matter and dark energy. And so we know that dark matter is not black holes. Black holes are still normal stuff. Antimatter is still normal stuff. Dust in between galaxies is still normal stuff. So dark matter is something, something else entirely. And we don't actually know exactly what it is. All we know is what it does. But one of the things that we are doing in experiments at the LHC is looking for signs of dark matter. We haven't seen any signs yet, but that doesn't mean that it doesn't exist. It just means that we haven't seen signs of it. We haven't been able to make dark matter yet in the LHC.
Thank you, madam.
Cool.
Hello, ma'am.
Hello.
My name is Lavanya. I'm studying 10th grade from Z.P.H.S Ilavaram.
Awesome.
I'm so delighted to take this opportunity. I have one question now. How did our universe begin and how will it end?
Ooh, great question. So how did the universe begin and how will it end? So this is a picture of the history of the universe. How did the universe begin? Well, long time ago, 14 billion years ago, there was nothing. And then all of a sudden, we had what we call, sorry guys, sorry. what we call the Big Bang. And basically, this was matter, energy, everything created in that moment during the Big Bang. Sorry, what was that?
Okay, okay, no problem. Carry on, carry on.
Hmm?
You carry on, carry on.
Oh, okay. Right. So that was the Big Bang. And we know that there was a beginning, because if you stand here today and you look out in all directions from us, you see galaxies and things moving away from us in all directions. So if you're seeing things moving away from us, then if you reverse time, then that meant that at some point in time, everything was all in one place. So that's how we know the Big Bang happened. Why the Big Bang happened is a very different question, and I don't think anybody can answer that at the moment. We don't know what there was before the Big Bang. In fact, in some ways, saying before the Big Bang is a sentence that doesn't make sense, because not only was matter and energy created at the Big Bang, time was created at the Big Bang. So, like, you can't have a concept of before something where when you only have the definition of time from this point on. But people like to imagine scenarios, and one thing that people think is, what if there was a previous universe and it expanded and then got bigger and bigger, and then it collapsed into itself, and then that bounced out and made the Big Bang from our universe. That is a possibility that could have happened. So then the other part of your question is, what's going to happen to our universe in the future? So the universe is expanding, but the universe is made of matter, and matter attracts each other from gravity. So up until like the 1998 or so, the thinking was that the universe is expanding after the Big Bang, but all the stuff in the universe is eventually going to be attracting itself from gravity, and the universe is eventually going to slow down the expansion, and gravity will pull our universe back together again into what we call a big crunch. But in 1998, people were looking at these supernova, measuring distances from galaxies away. And one of the things that they noticed was that the further away a galaxy was, the faster it was accelerating. So in other words, as things were getting away from us, they were going faster and faster and faster and faster and faster. And this means that the universe is not actually slowing down its expansion. This means that the expansion is going faster and faster and faster and faster and faster. So at this point in time, it looks like our universe is not going to come back together into a big crunch, but it's going to spread out and spread out forever. That unless something changes. Now, what is causing, so that's weird, right? What is causing the universe to expand more than it should, because gravity should pull it back, but it's not. And that is this thing that we call dark energy. But yeah, right now, it looks like the universe is just going to continue expanding forever. Another thing that we don't know is it going to continue expanding faster and faster and faster forever? And basically the universe will just be this huge, vast wasteland with, you know, very like cold and very little stuff in between? Or will it continue expanding, but the expansion will slow down until the universe just sort of sits there these are also questions for cosmologists and people who study space and things to try to figure out. We don't know. We don't know why the universe began, and we don't know how it's actually going to end. So it's a lot of fun things to study still in physics.
Thank you, ma'am.
Sure.
Hello, ma'am. This is Lakshya. I'm studying 10th class in Z.P.H.S Ilavaram. I feel privileged to interact with you, and I would like to ask one question. My question is, do you believe in the existence of aliens?
Sorry, say that again.
Do you believe in existence of aliens?
I'm not sure if I caught that one.
Do you believe in the existence of aliens?
Wait.
Do you believe in the existence of
Oh, aliens. Yeah. Ooh. That is so interesting. I think so. The universe is a really big place, right? I don't have a slide for this. I don't have a picture for this because, you know, there are no pictures yet. But so the universe is a really, really big place. There are gazillions of stars and gazillions of planets in the universe. If this is the only planet that randomly managed to evolve life, I think that would be really weird. I'm sure that somewhere out there, at least, there is type of life. It probably won't look like our life, but, you know, the universe is so big, it would be a awful waste of space if, you know, we were the only life in the universe. But another reason to believe that some kind of life is out there is just by looking at our own planet. If you go like right down into the deepest parts of the ocean, where, you know, the pressure from the water is huge and there's no light, but there's like a vent so the water itself is super cold, but then there's a vent from the Earth's crust, and you get like this hot sulfur bubbling out into the ocean. There'll be communities of bacteria and other little organisms living right there. And, you know, that's a really terrible place to live. But, you know, some kind of life likes to live there. That's the ideal situation for it. So, and, you know, and then you go to the poles where there's this permafrost and there's bacteria and things living in these areas too. So I think that there must be something else out there, just because life has this really remarkable way of, you know, figuring out how to exist, even when conditions are super high temperature or super high pressure or super cold or something like that. So yes, the aliens might not look like us, or they might not, you know, have those big heads with the eyes and things that you see in videos, but I think there's definitely life out there. Wait, do you believe in aliens?
Of course.
Hello, ma'am. I'm Saina. I'm 8th grader from Z.P.H.S School, Ilavaram. I feel great pride to interact with you, ma'am. I would like to pose your question tonight.
Yes.
What is dark energy?
energy, and why is the universe expanding ever faster?
I think she has already answered this question.
Well, I mean, I do have an extra slide for that question. So here's just a comparison between dark energy and dark matter. So the most amazing thing, right, is that even though we know so much about the universe, what we know is 5%. And there's 95% of the universe that we actually don't know about. And most of that is dark energy. So dark matter is stuff, but dark energy is kind of like a force. And it's a force that is pushing the universe apart faster than it should go. That is about all we actually know about it. We don't know why it's there. We don't know why it only really started, making an effect on the universe, in the last few whatever years of the universe's existence. For now, the thinking is that maybe it's some type of force or some type of field that lives through the entire universe that is causing it to expand. But yeah, that's maybe if you come and study cosmology at university in the future, you'll be able to answer this question.
Thank you, ma'am.
Sure.
Hello, ma'am. My name is Anteja. I am from Z.P.H.S Ilavaram. I am very happy today to interact with you. I would like to one question, ma'am.
Yes.
Could you please tell about a route map to become a successful scientist?
So this is an interesting question, because I don't think there is one magic formula that, creates a successful scientist. But I want to tell you, maybe give you an illustration of my path. So when you're young or something, you look at somebody else, you look at their life path, and you think that it looks something like this, right? Start off, I was interested in science when I was a kid, and then I went to school, went to university, it from the outside, things look like a nice straight line going there. In reality, this is what my life has looked like. So it's a big mess with ups and downs and twists and turns and things. This is what most people's path looks like. And perhaps the best advice I can give you is, don't be afraid if your path is doing that, because everybody's path is doing that in some way. What you can do is use each of these points along your path to contribute something to your life. So gain experience from each of these steps and use that in a way that, helps you do something that you love and enjoy and you're good at. If you love science, one of the lovely things about working in science is that you get to do something that you love. But there's also lots of parts of it that you don't particularly love. But because it's such a wide open field, you can really figure out exactly what are the parts that you really do like and kind of work towards focusing on them more. And then use that to really, that's what makes you become special, right? It's your own personal experiences that makes you stand out. because, you know, here at CERN, everybody is super smart and everybody knows a bunch of stuff. But what makes you special is maybe not like, you know, just the basic knowledge that you have. What makes you special is maybe you are super creative in computer programming, or maybe you are really good at, you know, debugging something, or maybe you're just really good at talking to people about physics. So take your advantage, take what you're good at and use them as advantages. That said, I do have, you know, just some basic tips. So study math and science, obviously, and try and do as best as you can at them. A very important thing for science nowadays is so much of it is computer programming related. So if you can do, I ended up not doing any computer science courses in school or university. So the way that I've learned how to program is, you know, reading other people's codes and Googling error messages and looking up stuff on Stack Exchange. But if you can do any programming courses or computer science courses, they will help you hugely in the future for any science. In addition, in particular, machine learning is becoming more and more used nowadays. You know, at the LHC, in our experiments, we're using machine learning to get better measurements of electrons, and, you know, to be able to get even more complicated types of events, looking for more complicated types of events. So while you're doing the computer science, while you're doing the programming, if you can also learn a bit about machine learning or AI, anything like that, that is a great, that will also help you hugely in the future. And then in particular, if you're interested in the Large Hadron Collider type of stuff, there were a few questions about the ATLAS experiment, but CMS is the other version. It's like the other version of the ATLAS experiment, and India is not part of the ATLAS experiment, but there are a lot of Indian institutes, universities working on CMS. There's a lot of Indian people at CERN working in the control room with me, doing stuff on the experiment, doing analyses. So, you know, you don't have to, you know, you can be part of LHC physics from right there at home. I've put the list, I think, on the computing of the groups down there at the bottom, and also, you know, there's a website here. Or if you just Google, you know, CMS experiment CERN India, you should find some stuff. And ask your teacher to get in contact with one of the lecturers or one of the professors at your local university, and see if they would like to come and, you know, give a talk as well about stuff. Another thing you can do is, you know, ask your teacher if they reach out to the universities. Maybe the professors at the universities have little projects or something that you can work on, or even, you know, summer projects and things. This all will give you additional experience, which, you know, it's not only good for your CV, but it's also good to learn whether this is actually something that you enjoy doing, or maybe, you know, you want to do something else in life. Cool.
Hello, ma'am. My name is Joshua. I'm studying 10th grade. My hobbies are reading books, playing games. I would like to ask a question, ma'am.
Mm-hmm.
Can a man from Earth settle on a Mars? Is there any planet which is similar to Earth?
Okay, so I mean, so settling on Mars, probably not as soon as people like Elon Musk want it to happen. because, you know, there's a lot of stuff. Okay. It's very easy to build a spaceship, put up a couple of people in the spaceship and send them off to Mars and let them land on Mars. It's going to take something like 4 years to get to Mars. But you know, that is doable now. The problem is keeping those people alive and healthy for the long term. So one big problem with space travel is you actually get a lot of radiation because our atmosphere, the Earth's magnetic field protects us from a lot of the radiation from outer space. But once you leave the Earth's magnetic field, then you actually get a lot of radiation, which does damage to our bodies. And when we're talking about long space travel, you know, like a few years to get to Mars, even people who live on the International Space Station for a year, their bodies will, get damage from this. So anything like that, this now becomes complicated to try to keep people healthy. And that's just getting to Mars. Then once you're on Mars, then, you know, we have to live and survive. And then stuff like terraforming and everything needs to happen. And these are really long processes. I mean, I don't know what the current feasibility is for that, but I think it's kind of a long-term thing. And interesting, if you've watched The Martian, that's a great movie to watch just to learn about like the challenges involved with, you know, a colony living on Mars. Is there a planet which is similar to Earth? So in our solar system, Venus is actually the same size as Earth, roughly the same size as Earth, but, you know, Venus has a really nasty atmosphere, and it's much closer to the sun, so it's super hot. It's it's unpleasant place to go. Mars is smaller than Earth. The gravity is less, but there is, but it's sort of the most stable in terms of climate, I guess. Otherwise, yeah, I'm sure, because there are billions and gazillions of stars and planets out there in the universe, I'm sure there's a planet similar to Earth sitting, nicely in this habitable region, close enough to a sun that's not too hot and not too cold, and it's a planet that's about the right size and has liquid water on it. I don't think we've found a planet really like that yet, but that's just because space is a very big place and these things are very far away, so it's hard to find them, even though we found something like more than 1,000 exoplanets. The problem again is getting there. And, really the universe is so big. So even traveling to the nearest star, light takes 4 years to get from the nearest star to us. And that's, traveling at the speed of light. And we can't go anywhere near the speed of light. So it would take thousands of years for a human being with our current technology to get to a different planet. So I think that it would be really cool to settle on different planets. The biggest challenge, I think, right now is just getting there in the first place. So if you like aerospace engineering, then that would be a fun thing to go study in the future.
So clearly, you have spent a very quality time with my students, answering to their questions so patiently, elaborately, comprehensively, using the slides. Thank you so much for your time, and we thoroughly enjoyed the session. We look forward to witness the the scientific process in Atlantis. So we are so excited to witness that to live. So could you please give us a few dates, maybe in your convenient time, and we look forward to meet you again in virtually like this, and to witness the exact process that is in progress in the project of Atlas. So for time being, we would like to request my students to sing our national anthem. Because
Awesome.
it is our honor to host your session, because we consider you as the greatest scientist that we have ever interacted virtually. So thank you so much again. Students, come together.
Thank you so much, all of you. And thank you for the really amazing questions. They were great. And I hope to see some of you working at CERN in the future.
Yeah, sure. So come together. 3, 2, 1.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे गाहे तव शुभ आशीष माहे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Before we wind up the session, could you please give a final message to my students? Final message, please.
Final message. Thank you all for being interested and asking questions. I think the most important thing in life is to just keep asking questions, keep seeking answers, and yeah, don't let anybody discourage you from doing that. And I love your South African flag in the back.
Yeah, yes.